Welcome to question 9 of the 2007 Mathematical Methods Exam 1. In this video we will be looking at the solution and examination advice for this question. A reminder that this video is in no way endorsed by VCAA. The graph of f with a rule f of x equals e to the power of x over 2 plus 1 is shown. The normal to the graph of f where it crosses the y-axis is also shown. So a normal is simply perpendicular to a tangent at the same point. And for part A, we're asked to find the equation of the normal to the graph of f where it crosses the y-axis. So because we know that it's perpendicular to a tangent line, if we find the gradient of a tangent line, we can find the gradient of the normal line. And to find the gradient of a tangent, we're going to use the derivative. So f dashed of x is going to equal, and if we have e to the power of x over 2 plus 1, the derivative of that is simply a half e to the power of x over 2. Therefore, f dashed of 0, so the gradient of a tangent at x equals 0, where it crosses the y-axis, is going to be a half e to the power of 0, which is simply equal to a half. So that equals the gradient of a tangent line at that point. Now we know that the tangent and the normal are perpendicular, so we know that the gradient of the normal times the gradient of the tangent is equal to -1. Therefore, the gradient of the normal line is equal to -1 divided by the gradient of the tangent, which was found to be a half, which equals -2. Next up, we need to find the y-intercept of this graph. So if we find the y-intercept, that's done by letting x equals 0 in the rule for the curve. So therefore we have f of 0 is equal to e to the power of 0 plus 1, which is equal to 1 plus 1, which equals 2. So this point here, that is the y-intercept, has the coordinates 0, 2. So now that we have the gradient of the normal and a point that line passes through, we can use the equation y take y1 equals m bracket x take x1 to find the equation of that straight line. Therefore, substituting in what we know, we'd have y take y1, which is 2, is equal to the gradient, which is -2, and then x take x1, which is 0. And then solving for y, we'd have y take 2 is equal to -2x. Therefore, y equals -2x plus 2. So that is the equation of the normal line to the curve f when it crosses the y-axis. So from the examiner's report, we can see that 44% of students got this question correct, and the comment was that students often had difficulty correctly finding the y-intercept, with 0, 1 being a common answer. That led to a normal being y equals -2x plus 1, which was incorrect. Quite a few students differentiated, but then did not find the value of the derivative when x equals 0, simply substituting in the expression for the derivative into the equation of the normal, which led to incorrect attempts at algebraic manipulations and non-linear normals. Some students found a tangent line instead of the normal line, which was required for this question. So for part B, we're asked to find the exact area of the shaded region. So for part B, we're asked to find the exact area of the shaded region. And from part A, we know a few things. We know that the equation of this normal line is y equals -2x plus 2. We knew that this point here, the y-intercept, was at 0, 2. And using this equation, if we let y equals 0, we find x equals 1. So that point there would be 1, 0. So next up, we can remember that we have a way of finding the area between two curves, and between the terminals of A and B, the area is given by the upper curve minus the rule of the lower curve with respect to x. Therefore, for this question, the area is going to equal the integral between the lower limit of x equals 0 and the upper limit of x equals 1. For the upper curve, which is f of x, which has a rule e to the power of x over 2 plus 1, minus the rule of the lower curve, which is the normal, which has a rule minus 2x plus 2, and we anti-differentiate that with respect to x. So simplifying this, we find that that's the integral between 0 and 1, And if we do the subtraction, we'd have e to the power of x on 2, and then we have plus 1 and minus 2 would give negative 1, and then subtract negative 2x would give positive 2x dx. So that means that the area is equal to the antiderivative, so e to the power of x on 2, the antiderivative of that would be 2e to the x on 2 minus x plus x squared, evaluated between 0 and 1. And we know we can evaluate that by evaluating the antiderivative at 1 and then subtracting away the antiderivative evaluated at 0. So substituting 1 into that expression would give 2e to the power of a half minus 1 plus 1 squared is 1. And then subtracting away 0 substituted in there, we'd have 2e to the power of 0 minus 0 plus 0. So that would be all that's left in that second evaluation. However, we know that anything to the power of 0 is simply 1. So that gives the area is equal to 2e to the power of a half, 2e to the power of a half, minus 1 plus 1 is 0, and then we'd have minus 2 times 1 is minus 2. So that is the value for the area bounded by the curve and the normal between 0 and 1, which is the shaded region on the diagram above. So we can see that approximately a quarter of students got this fully correct, and the examiner said that most students could correctly set up an area expression, but some were unable to proceed because their normal was not a linear expression. Many had the correct terminals, although 2 instead of 1 was a popular incorrect value for the upper terminal. Arithmetic errors appeared frequently, and subtraction mistakes were common for that integrand. Some students also lost 1 from the equation of the curve, which was in this position here. The use of dx was surprisingly good, and students are reminded that that's part of the correct notation when doing these sorts of problems. And finally, a few students used the area under the curve minus a triangle with some success.